here then. Okay. Are you going in person, or are you doing remote learning?
In
Like
person.
in person? Okay. All right. Well,
But
all
we
right.
learned this unit remotely, so that's fun.
Yeah. Yeah, it's a real mess. Okay, well, I'll just start working through these, and then I'll try to instead of talking, write the things that I think you would want to remember. So uh, this and there's a picture on the right on the left. Generally, there's a box here, and it's like when you're looking up, this is the angle of elevation, alpha, and this is the angle of depression, and that's beta, and they're equivalent, they're equal. These angles are the same because if these lines are parallel, they're cut by a transversal. This is geometry. These alternate interior angles are congruent. So what happens is sometimes they give you uh, one or the other, and you need to use one or the other. Hang on just a second, please. 30 seconds. All right, I'm back. So sometimes they give you one or the other. I don't know. Is this something you've seen before?
Yes.
Okay, so this would be the kind of thing I would put in your notes. Maybe this picture or something that conveys this to you. I wouldn't draw my picture. I would draw something that meant something to you.
That sounds good.
Okay. Sorry. Are you generally quiet, reserved, private?
Um,
I can't see you. That's what I'm trying to figure this out with you, because almost everyone I help now I've seen in person, and I kind of know their ebbs and flows.
I'm usually pretty loud, but
Okay.
Zoom and math,
I
I'm
see.
not loud
I
in math.
see. I see. So I'm here to serve you. So if you don't think I'm doing a good job, you should tell me that I'm not. You didn't understand. That wasn't clear. Verbalize it. I will not be. It will not hurt my feelings. It will not. I want to. I want to make sure you're happy. You are my customer. I want to make sure you get everything you can out of this lesson. That's why I have to ask more and more, because I want to make sure you're getting what you want out of this. And you know, convey to me what you want, and I'll do my best to meet that at this point.
Yeah, this is really helpful. Just like
Okay.
going through it with explanations is good.
All right. All right. So we're talking about harmonic motion, and that is things that tend to oscillate. So things that go up and then down and then up, or like we saw with cosine. Actually, this is something else. This is a sine wave. Definitely have this in my notes. And I'll even label it 2 pi, pi, pi over 2, 3 pi over 2. This is 1 and this is -1. I definitely have this in there. And then a cosine wave, well, it starts high, goes low, comes back up, and goes high again. So this is a cosine wave. These go forever. 2 pi, pi, pi over 2, 3 pi over 2. This is 1, this is -1. I definitely have this kind of in there. So things that are harmonic motion, those are things that you could think of them as repeating. Some sort of motion that you see, it does the same thing over and over again. So it doesn't have to necessarily just be something that goes in a circle. A piston in a car does go up and down. Pistons go up, they go down, they go up. Springs, they go up and down. I don't know, your wheels that are turning, anything that's turning, like your wheel, those are not your steering wheel, your the actual wheels and tires in your car. Those can absolutely be simple harmonic oscillators. Now your instructor might emphasize like no friction or air resistance. Um, so have you ever, do you know what a slinky is?
Yes, I do.
Okay.
Like the reason that like a circle is like harmonic motion is because it like when you unspool it, it's like a like it's just like a sine or cosine. So it's like right?
Yeah,
Is that right?
these are all related. Like yes, those are related back and forth. In terms of a harmonic oscillator, like you get back to the same position, just like a piston goes down, goes up, goes down, goes up. You always get back to the same position. Okay, but not everything does that in the real world, and that's why your instructor says no friction, no air resistance. So Slinky maybe is not the best example, but a pendulum is, if you had if they call these things perfect pendulums. A pendulum, if you have a grandfather clock in your home, it swings, from one side to the other. That's probably a better example. Do you have one of these in your home, grandfather clock?
I
I don't,
know, but I've seen one.
okay, so if you let them run and you don't wind them, they will eventually stop because there's friction in them. So the friction is what causes these things to eventually go to where they're not moving at all. They're very little moving back and forth. The Slinky is supposed to be a perfect simple harmonic oscillator, but eventually it doesn't have enough energy or momentum to like keep going down the stairs because there's internal friction or resistance. So there really is no such thing as a perfect oscillator, but your instructor may ask you a question like, well, what might happen? This is really advanced, but what ends up happening is if you have an oscillator like a sine wave, and there's friction, what it does is it compresses like these motions, and then over time it just kind of settles on the origin there. And that's what's happening with this pendulum here. Like as it stops going back and forth, it doesn't oscillate as much. It just kind of stops doing anything.
Yeah, I understand
Okay,
that. Okay,
great.
that sounds
Okay,
good.
so
It's
see,
like
I think
in the
that,
real world, there is
yeah, that's in the
friction
real world.
and
Yeah,
resistance,
so that's kind of,
so it like loses momentum.
yeah. Another kind of, if I don't know if you ever driven your car in such a way where you let your foot off the gas, but if you're going up a hill, eventually your car stops moving. And that's because the friction is working against your vehicle, which is trying to move forward, but there's not enough forward momentum of the car. The hill's too steep, and you don't move. All right, here's a word problem. Oh, I guess that was a question I should ask: is are the word problems you see in the exam similar to these, or are they completely different?
Yeah, they're really similar to those.
Oh, good. Okay. So if it were me, I'd probably really have good notes on the ones that are here. So an airplane flies out of Kennedy Airport at a speed of 450 miles per hour and a course of 320 degrees. Okay. I don't want to be confusing, but there's these nautical problems, airplane problems, where it's 320 degrees from true north. Do you remember in class if you were doing it from true north, or what is also common is from the unit circle where you start there? Like in this case, that's 0 degrees. This is 0 degrees. Yep. Do you have any idea? And it doesn't
Um,
matter because we can use either one, but I want to be consistent with what maybe you're doing in class.
I would assume unit circle.
Okay, so let's say unit circle here, 320 degrees from the unit circle is, all right, I got 0, I got 90, 180, 270, and then back this way, 360 is all the way around. So 320 is pretty close to coming all the way back around. It's going this way. So that's the angle, and you're traveling this way. Okay, traveling that way. Now you're going 450 miles per hour, and you do that for 30 minutes. Okay. Now these numbers are a little bit large, but it's like saying you drove your car 45 miles per hour for 30 minutes. How far did you go? Or if you don't like that, we can come up with some other numbers. But do you know how to convert the rate and the time to a distance? I'll give you a hint. You just multiply the rate and the
Um,
time.
yeah. So like do like 450 MP, like 450 M over 1H.
It's a little bit simpler than that. It's miles per hour, and then 30 minutes is really
Point 5 hours.
0.5 hours exactly. Okay, so so you've gone 225. They've gone 225 miles. Okay, then they change course. They change course 230 degrees. Okay, so how this could be maybe confusing is if I start from here and go 230 degrees, I'm over here somewhere. What is the angle between 230 and 320?
90?
90. You shouldn't be surprised by that because all you know about in your world is right triangle trigonometry. And that's what we've got here. So you got a triangle here. So you turn this way 90 degrees. So you've gone 225. You turn and you fly for another hour. So it assumes you're at the same speed. I don't know if that's reasonable or not, but because you can't change that quickly. But in 1 hour you go 450 miles. Is that okay?
Yeah, that's good. I
Okay.
understand that.
So we started here and we're now.
You're making, sorry, it's like you're making a new unit circle around the end point of the 225.
You could, yeah, I mean that works. But it's not wrong. I'm just trying to give you a visual like what's going on here.
Yeah, definitely.
So you go 225, then you turn and you go 450, and well, it's not drawn correctly. We need the distance here. So how do we find the third side of a triangle? Pythagorean theorem. So this is something I would put. I used to do this a lot. I box stuff in that you definitely would like to have on there. Although maybe by now you know that it only works for right
Yeah,
triangles.
I think I know that. I think I know that one.
Okay.
That one I know.
All right, great. So you got 225 squared plus 450 squared equals c squared. Okay, so that's the distance part of this. You have to solve for c. So c equals the square root 225 squared plus 450 squared. So you get a number, and that's what it is.
Okay, that sounds good. Yeah, that makes sense.
So it's
It's all
bearing
about
though.
getting the right model.
Yeah, you got to draw the picture. So you're to me it like I don't know. You were going 320, you backed it off 230, so it's to me you're heading straight south, I guess. So it could be. Well, unless so sometimes see what I'm not sure about is do they want an angle or do they want this, I don't know, do they want the angle here? Really not sure.
Can I see the question again?
Yeah, they just want the plane's bearing and the distance. We got the distance.
What exactly does bearing mean?
It's an angle, but it's an angle relative to something, and that's what I'm.
Interesting.
Yeah,
Well
so maybe
thought
just check with
out.
your instructor on that. You know, kind of what they're looking for there, because there's a lot of ways to answer that, and I don't know exactly that. I've given you the complete answer, but okay, let's look at number 5. Okay, and then what I should say again is like what you should take away from a problem like this is can you draw this picture? So geometry specifically, I know you're in pre-calculus algebra 2 trigonometry, something like that. You don't get the picture, so can you draw the picture? You know, are you comfortable drawing a picture? These ones with airplanes or ships, they're often a little bit more challenging to draw. Without the right picture, you know, you're just totally stuck.
The
For that.
nice thing is that she like gives a lot of like pity points. So
Oh,
like if you have the general idea and like you put some good like conceptual stuff in, she'll give you a decent amount of points and she usually curves it. So
okay.
that's very
Okay.
good.
Good. Good. Okay. So we kind of talked about this in first primary, the angle of elevation. So angle of elevation means you're here, you're looking at something above the ground, and your first angle of elevation is 25 degrees. So there's an airplane coming towards you. I don't know, it's weird, but okay. The airplane's coming that way. If the plane's altitude is 2,500 feet, okay, That's what that's referring to. How far is the plane's travel? Okay, so then, so the later time, this is where it's a little weird. So the plane doesn't descend, it's now here. Okay, there's a new triangle, and this angle is 65 degrees. Is that okay?
Yes. So we know like the angles of elevation for both of them, and we
Yeah,
know we know two angles of each triangle and one side length for both of them.
yeah, and what I'm going to do is I'm actually going to draw them as separate triangles because it's rare when you actually like want to overlap lines. So in one triangle, this is 25 degrees and this is 2500. So in the first and sort of like part one, the plane is you look up there, you see the plane. Can you calculate this distance x? Yes, yes. And that comes from knowing sine, cosine, and tangent. So again, you asked like, hey, what do you write down? Well, so katoa, whatever other way you know to remember this.
Some old hippie caught another hippie tripping on acid.
Wonderful. Okay.
Yeah.
So you've got this down. Now, more importantly than that, though, is you need to know, well, how do I apply this? Because that's what your instructor really is testing on. They're like, okay, if you can draw this picture, which trig function to use? So relative to this angle, what is 2500 and what is x? And your choices are opposite, adjacent, and hypotenuse. So it's 25. Go ahead.
X is adjacent,
Good.
25 is the angle, and 2500 is the opposite.
Right. So opposite and adjacent. So which of these three uses opposite and adjacent?
Tangent.
Tangent. So the tangent of 25 is the opposite over the adjacent. So there's only one variable in this. So your variable is x. To solve for x, you can cross multiply. You can do a lot of things here. I'll just cross multiply, and x, then you divide both sides by tangent 25. So this is where your calculator has to be in degrees, because this is in degrees. This is where you have to check your mode and make sure you get that. So that's how far the away the plane is at that first instant moment in time. But later on, we got this other triangle here. Well, you can call it x if you want. I'm gonna write. Actually, I don't really like that. I'm gonna use that d for that. Let's call that d. We're gonna do the same thing. So relative to 65 degrees, you have the opposite and the adjacent. So the tangent of 65 degrees is 2500 over d. So to solve for d, cross multiply. So d equals 2500 over tangent 65. So you're going to get two numbers. And you shouldn't be surprised. This x is going to be larger than this d because it's coming closer to you. And then what it's really asking for, that's where you go back to the question, how far does the plane travel? So what we're looking for is this distance right in here. Well, it's the difference in the two distances. This is x minus d. X is the whole length, d is the length.
Is it just like 2500 tangent 65 or like whatever that was?
Oops, why did I put the wrong angle? Oh, yes.
Oh, yeah, 2500 over tangent 25 minus
yes.
2500 over tangent 65.
You got it. So I'm throwing this into my calculator, and I will give you what I think the answer is, and you can confirm it or just accept it. 40. So that the x minus d ends up being 4195. I don't know, feet. Yeah.
That would make sense. Yeah.
Totally reasonable. Okay. So the question. Okay, the one that you normally see on tests. This is actually a much better version of what you normally see on tests. The standard test question is you're looking at a mountain or something, and you're like, oh, it's 15 degrees. Then you move 200 feet closer, and you're at 65 degrees, and you know that the height of this thing is like, I don't know, 500, for example. This is kind of related. You can kind of see there's two triangles again, and they want to know. I don't know. They usually want to know like the total distance or something. So you have to find this, and then you find the total distance by adding together. Sometimes they don't give you this number, and you can still solve for it. But it's kind of a variation on the same problem here. Okay, that takes
Yeah,
care
I
of.
think the place where I would definitely mess up is choosing which like trig function to use.
Okay, so we could just really quickly draw some triangles here. Let me give you this, and let's say I tell you that x and 12. Okay, so which trig function would you use, and how you decide is relative to this angle. What is x and what is 12? And your options are always opposite, adjacent, and hypotenuse. So what is x? Is it opposite, adjacent, or hypotenuse?
Hypotenuse.
By the way, those are always legs. 12 is
The adjacent.
adjacent. So which trig function uses the adjacent and the hypotenuse?
The cosine.
Cosine. So you write cosine of 25 degrees equals adjacent 12 over x. Are you comfortable solving this for x? Meaning, like, can you get x by itself? Are you okay to do that? Great. Okay.
Where did like secant, cosecant, and all that stuff come into play?
Well, this is actually a perfect problem to use them. Secant you actually never use them in this context, but secant is 1 over cosine. So 1 over cosine here is the flip of this. Like 1 over this side is 1 over this side, and 1 over the right side is x over 12. But instead of writing 1 over cosine, you can write secant. The issue, though, is you don't have a secant button on your calculator. And if you had a really sophisticated one, you still wouldn't use secant. You would always use cosine. So generally, the way that secant and cosecant and cotangent are used is they give you a triangle like this. They say, okay, this is 10. This is 6. What is c? Let's first find c. So 6 squared plus 10 squared equals c squared. So you get 36 plus 100 equals c squared. 136 equals c squared. Take the square root of both sides. Square root of 136, you have to break it apart. 2 and 68, 2 and 34, and it no longer reduces after that. Let me know if any of that's unclear. So that's 2 square root 34. So now, like, I can give you angle A and angle B, and you could get a problem that says, what is the secant of angle A? And there's 2 ways, I think, to do this. The first is to know that secant is cosine is the adjacent over hypotenuse. Secant is the flip of that. And I don't think that's very clear. If you know that secant is 1 over the cosine of A, well, what is cosine of A? Well, you know that because you know it's adjacent over hypotenuse. So what do you do when you have 1 over a fraction? You flip the fraction, right? So it's 2 square root 34 over 6. And these cancel out, so it'd be square root 34 over 3. Okay, now we could find cosecant of angle A. And if you're, if you know your trig relationships really well, you can just read it off. But I don't try to remember those. I try to say, okay, well, what is it in terms of sine and cosine? Well, it's 1 over sine A. Well, what is sine A again? It's opposite over hypotenuse. Let's go back up to the triangle. Relative to A, the opposite angle is, opposite side is 10. The hypotenuse is 2 root 34. So it's 10 over 2 square root 34. Whenever you have 1 over a fraction A over B equals B over A, you just flip the fraction on the bottom. So it's 2 square root 34 over 10. And then 2 goes into 10. So you can write that like this. So that's generally how it's used. Just remembering back what your review had there, it also talked about vertical asymptotes having to do with secant and cosecant. I can cover those if you'd like.
Yes, definitely. She asked a lot about asymptotes. That would be great. Yeah.
Okay. So let's transition on to that then. Okay. So let me give you, let's say that I give you a function. I say f of x equals 2 minus cosecant 2 pi x. Okay. So one of the things that you've got to be very comfortable with is period. The period for the following: sine, cosine, and because these are related to cosecant and secant, is always 2 pi over b. B is the number in front of x, or t, depending on any here. So your b is 2 pi. So the period for this thing is 2 pi over 2 pi, which is 1. Okay, so you need to know that because that helps to figure this out. All right, now you asked about vertical asymptotes. The reason this thing has vertical asymptotes is because whether you're graphing a sine or you're graphing a cosine, wherever these things have mins and maxes, your related graph has this U shape. Hopefully you've seen that either graphically or in class.
Yeah, I've seen that.
Okay. But where it crosses the axis, those result in these asymptotes. Oops, that last one was not drawn properly right in there. Okay. So vertical asymptotes of this function, which is 2 minus, what did I say, cosecant 2 pi x. We're not looking at this. We're looking at 2 minus 1 over sine 2 pi x. So you always convert this to its sine or cosine equivalent. Now from previous part of this class or another class, that one of the things you can't do in math is divide by 0, because when you divide by 0, it produces a vertical asymptote. So you need to figure out, where does this thing equal 0? Where does sine 2 pi x equal 0? So it's a long-winded way of how to do this, but that's what you're trying to figure out. So there's a common technique in math which is called a U substitution. Where does the sine of u equal 0? Or if you're not comfortable with this, where is the sine of x equal to 0? So if you go to your unit circle, I'm asking you, where on the unit circle does the y value equal 0? And you should say
90 degrees and 270 degrees.
The y value.
Oh, duh. Okay. 0 degrees and 180 degrees.
Okay, so we're
also known as 0 pi and 2 pi.
0 pi and 2 pi, and it goes on forever, right?
Yeah, like
3 pi, 4 pi, and so on, right? Now this is a nice case. This is a nice case because what is the jump between each of these?
90 degrees. I mean,
pi. Yeah, you're gonna break yourself of that eventually. So the answer here is when u is equal to a multiple of pi, we're good, right? So maybe have you seen this in class, n pi or k pi? Have you seen that?
It's all coming back. Yes.
Okay.
Yes.
Okay, so we're going to say u equals n pi, and n means it goes, minus ... -3, -2, -1, 0, 1, 2, 3. Sometimes instructors say element of the integers. The point is n is this like repeating thing. Okay. Now we've really dug down into this question, but we solved it for sine of u equals 0. but we're not doing it for u. What is u again? U is
2 pi x.
2 pi x.
2 pi x time. Oh.
Okay, so whenever you make this u substitution, the step we just made is when you back substitute. That's what we did right there. You substitute and then you back substitute. And here you solve for x. Okay, so you get x equals n pi over 2 pi. The pi's cancel and you get n over 2. We're going to do another one, but this is key.
So it's just like a vertical asymptote occurs whenever x equals n over 2.
And n is an element of the integers, or this setup here that is the integers.
Right. Okay.
Okay, so it's like 1/2, 2 halves, 3 halves, 4 halves, 5 halves, and so on. Okay, let's do another one here.
Yeah.
All right, let's say you a function. I tell you that it's 3 secant 4x minus 2. First thing we're going to do is find the period. What is the period of this? It's 2 pi over b. The b is 4, so it's pi over 2. That's just a side thing. It's not really relevant to what we're doing, but I want you to be comfortable finding periods. So f of x is 3 times 1 over cosine 4x minus 2. Again, there's only really 2 things you can't do in math. One's divide by 0, the other's take a square root of a negative. These are like not allowed. They're allowed in some other worlds, but not this one. So where does this bottom part equal 0? Where does cosine of 4x equal 0? And that's hard, but if you make a u substitution, if you say, well, I'm going to let u equal 4x, can you figure out where cosine of u equals 0? Yes. Where on the unit circle is the x coordinate equal to 0? You had this before. It was pi over 2, 3 pi over 2, and so on, right?
Yes.
Great. So it's pi over 2. The answer, like this, how do we express this? This is pi over 2 plus k pi, or n pi. I'll use k this time. Actually, let me use n to be consistent. N pi. So like the jump here is pi, because the next one is 5 pi over 2. If you go back this way, it's minus pi over 2. The jump is always pi, and that's what this means. 1 pi, 2 pi, 3 pi, 4 pi. You're always jumping there. But go ahead.
Okay. How do you know when it's like when x is 0 or if it's when it's y is 0?
So the x coordinate is always cosine, and the y coordinate is always sine.
Oh, I see that right underneath the unit circle on the trig cheat sheet for
Good.
Right there. Wow.
Yep.
Okay.
It's really critical that you know that and that you're comfortable with that. And a lot of ways to remember it. I remember that C comes before S in the alphabet, X comes before Y. That's my way. You can use anything you want to come up with that. Okay, so what we did though is we did it for cosine of u, but that's not what we're doing. We're doing 4x. So u is equal to this, and this is where you have to back substitute. It's not u, we care about 4x. 4x equals pi over 2 plus n pi. It's very important that you write this period because you divide both of them by 4, not just one of them. So this is pi over 8 plus n pi over 4. That's your answer there. We can do more examples of these. They get more difficult from here. I would try to figure out how much more of this was going to be on the exam before I spent a lot more time on this. But it's up to you. You tell me where you want to go. There are some. Go ahead.
Oh, sorry. I feel like this was a good prime, like general overview of it.
Yes.
Yeah.
Because I can make questions harder than this, but I don't know what your instructor is going to give you. I wish I had some more to help you.
If I know the basics, I can write enough that she'll give me enough points that I can get the grade that I need.
Okay. I like it. I like it. That's what college students do all the time. All right. Okay, so where should we go from here? Because we've done all the word problems. 4.1 is not really word problems. They're sort of concepts. 6 kind of is on 4.1, a word problem. But what else would you like us to cover in the time we have remaining?
Let me take a look. See, let's see. I'll go to the notes that she has and see if anything was emphasized.
Okay.
Let's
Do any of her notes, does she ever sort of emphasize or, asterisks, or sometimes they really bold or underline things that are really critical that they want you to know?
They're all kind of the same font and all that. Oh, can we go over like um just like kind of basic function analysis and transformations and like sine and cosine graphs?
Yes. Okay. Do you have that trig cheat sheet up
Yes, I do.
okay. So on page, I'm getting to where I've got mine up. On page 2, do you see the cofunction formulas there on the lower right?
Yes, I see it.
Okay, so we're only going to look at 2 of them. But if you graph a sine wave, okay, a sine wave goes up and then down and up, and then a cosine wave, I graph it right on top of it. Starts high, goes low, and then it comes back up. If you move the sine left, you get a cosine. If you move the cosine right, you get a sine.
Yes.
Okay, it's just moving those things over. So this is where kind of this, like, you're like, I didn't know this. There's really only one function. It's either sine or cosine. You can build everything else out of the one or the other, because it's just a shift in that. And that's what these cofunction formulas are telling you. They're like, okay, well, you think you want a sine? Well, your sine is really a cosine of 90 minus that one. Pi over 2 is 90. Oh, you want a cosine? Well, it's sine of 90 minus that. They're just shifts of one another. Okay, so that's kind of a basic thing here, that you can manipulate a sine or a cosine to become the other. That was kind of that F and G on one of the practice problems, where you can write any graph as one or the other. Okay. So before we go to looking at trig functions, I always like looking at x squared. And we're going to go through some of these. If I say x minus 2, which way is the shifting? Up, down, left, or right?
It's to the right.
Right, 2. Okay. So
Minus.
the equivalent one here is, let's say I give you a sine of x, and I say sine x minus 2 pi. Which way does this go?
Right by 2 pi.
Right by 2 pi. Very similar. So if it were x plus 3 squared sine x plus 3 pi, this would be 3 pi left. So inside is left or right, and hopefully that's clear. Now, if I say x squared plus 4, that's like me saying sine x plus 4, it's 4 up. Sine x minus 3 is 3 down. What does a negative do to an x squared?
It
So it is going up, and then this causes it to go.
It flips it.
Okay.
It flips it horizontally. Yeah.
So the problem is there's not really a direct thing for that, because negative sine x equals sine of negative x. Okay, so not everything works perfectly, but the ones that you care about next, like what is 2x squared? Well, it scales it by 2. 2 sine x is a scale of 2. So kind of I'll throw everything at you here in one question. If the parent function is y equals sine x, and I give you the following, if I give you a y equals 2 sine 2 pi x minus 4 plus 3, what are the transformations of this? So before you can do that, before you can even answer my question, which is what are the transformations? What transformations? You have to make a small change. So if I write the sorry, if I write
Oh, you
the
have to like factor that out. So like
yes,
I would
because it's written
say
like this, and this isn't really helpful because you really need to factor this. It's really C over B here. And this is the phase shift, but yeah, so in your problem here, you need to factor out 2 pi. This is where it's a little bit harder. You're like, what goes here? Well, it's whatever you multiply in has to give you 4. So 2 times 2 gives you 4. How do I cancel the pi's? Well, I have a pi on the bottom. If you don't like that, you can say, well, call this x. 2 pi times x has to equal 4. And then you divide both sides by 2 pi, and you're like, oh, it's 2 over pi. If you don't like just kind of guessing and checking. Okay, so this right here is the phase shift. This is the equivalent to like the parabola number inside parentheses.
so it moves right by 2 pi.
2 over pi.
2
And you
over.
have to be very clear. If you say 2 pi right or right 2 pi, this number is used for the period. This is like compressing or expanding it. So you always use this number to get the period. The period is 2 pi over b. In this case, b is 2 pi. I shouldn't keep using that number. 2 pi over 2 pi, so that's 1. That's the stretching of this horizontally or vertically. So I think you've seen some graphs, pictures of graphs where some take a really long time to get done. Oops. And then some are really, in here like that. And that's all based on this number here.
Okay. Yeah. So like it doesn't like previously with like non-trig functions, when you change that, you're like, oh, it's a vertical stretch or vertical shrink, but this is like a period change, and you can describe it as that.
It's a horizontal stretch,
Okay, horizontal
but
stretch.
the correct word used here is the period. Like period includes an understanding of horizontal stretch.
I see.
So let me so this is kind of a conceptual question. If the period is 2 pi, and that's a normal sine or cosine, if the period becomes 4 pi, do you get more or less of the sine waves in either one? Like you have to kind of answer that question. Like, and here's
You get more waves like per set different distance with a period of 2 pi than 4 pi.
So if your period's 2 pi, you get 2 of them, whereas here you only get probably even drawn right. You only get 1. So you're right. So you get 2 of these for 1 of these, and that's the horizontal stretch. That's what's implied by that. This plus 3 is the same as before. It shifts up 3. This 2 is a vertical stretch. This is a vertical stretch. That's the amplitude.
Okay. Ah, yes, amplitude. I know that word. Yeah.
Good. Okay, so I haven't really had you do any problems. I'll have you do one here. Y equals minus 3 cosine 1/2 x minus pi plus 2. And I want you to factor out a 1/2. And then I want you to tell me the period of this thing. And give yourself like 60 seconds to figure it out.
I am so sorry, but I forgot. Is B the number that is before or in? Okay, that is B. Thank you. Got
Yes.
it.
What number goes in this position?
I want to say C.
uh, okay, this is actually C here. I'm laughing because I was unclear. Um, I got to be clear on this. It's bx plus C or minus C, but this is not C, but it is the phase shift. So it's kind of incorrectly labeled. This is your phase shift.
Okay.
It's not pi. Like a lot of times you think, oh, C is the phase shift. It is if B is 1, but B is not 1. It's 1/2. And I was asking is like what number goes in there after you factored out the 1/2.
Okay, well, I did get 2 pi for that.
Okay, so
So
it's
then I
2
would
pi.
set
Good.
1/2. Okay, so I would do P equals 2 pi over 1/2.
Yes, your period is 2 pi over B, 2 pi over 1/2. So if you have A over a fraction like 1 over big B, it ends up being B times A. So
Okay, so
you're
it's
on to the
just 4
top.
pi.
Yes, 4 pi. So that's your period. Um, the three, stretches it vertically. The negative flips it over the x-axis. It's a reflection though. It's not really a flip. It's a reflection. And then the 2 is going up 2 units.
Okay, I get that. That makes sense.
Great. So
This
go ahead.
Oh, never mind, never mind.
We're right here at the end of the lesson here. So I'll send you out the notes and the screen recording here shortly. Thanks again for scheduling. Again, if we're kind of just working together again. So always let me know if you need me to stop talking or do more on one or less on another. I totally here to serve whatever you want as far as getting through this content and understanding.
Yeah, for sure. I definitely wanna make this a more regular thing unless, oh, I'm about to have a midterm. So, I'm gonna work on that.
Good. And ask your teacher questions. You know, they really get excited when students ask questions. So even if it's something we already covered, just ask again, and I'm sure you'll get even more information. And,
Okay, that sounds good. Thank you so
all right.
much.
Have a great night. See you next
You
time.
too. Bye.